Okay, so today we will start where we left off last time. So remember that last time, maybe I should switch these lights on. Yeah, it's better. And just a moment. Yeah. So remember that last time we solved the Laplace equation in 1 dimension, 2 dimension and 3 dimensions. In 1 dimension it's trivial, so I'm not going to write it down, but in 2 dimensions, again we noted that it was easy because all of us know complex analysis, and all we needed to do was to write down the real and imaginary parts of monomials of z, right? So, or zeta. So we found the solutions to be rho to the L equal to plus minus I of I, right? And in 3D, we use the Herglotz trick to write down all of the solutions as R to the L by Lm of whatever, okay, by the Herglotz trick. Right. Yeah. Okay. So we're done with solving the Laplace equation. Today what I want to do is to solve the eigenvalue problems of the Laplacian. Okay. In particular, I want to solve, so today we will now solve the positive and the negative eigenvalue problems of the Laplacian, which look like this and this. Right? Now some of you might already say, oh, you just need to solve this and then you can analytically continue to solve that, right? Which is what we do, okay? But these two are what we'll be interested in today. Now remember from a few classes ago that I told you that all of these things will become interesting to us. Why we're sitting down and solving all these equations now is because the same equations will come back to us time and again when we start solving electromagnetism problems. For example, such equations will come up not just in radiation problems where you will think these will obviously show up because it's a Helmholtz equation, but it also shows up in electrostatics, as we will see, because Laplacians are ubiquitous and eigenfunction equations for Laplacians are also ubiquitous when you do separation of variables, for example. Okay? Okay, so this is the positive eigenvalue problem of the Laplacian, this is the negative eigenvalue problem of the Laplacian. I will take kappa to be real. And this is usually called the screen-Poisson equation. And this is called the Helmholtz equation. Right? So now we want techniques to solve these two equations. In particular, today I will be interested in the spherically symmetric solutions of such equations. Okay. By which I mean, if you're solving the 3D problem, say the Laplacian you're taking to be 3D, spherically symmetric basically means that the solution must only depend on R. If you're solving it in 2D, the spherically symmetric means that you are only dependent on the radial coordinate, which on the plane I will take to be always rho. Okay. So that's what I mean. And if you're doing it in higher dimensions, it basically means invariance under the higher dimensional sphere. If you're in RD, if you're taking the d-dimensional Laplacian, spherical symmetry basically means that it's invariant under rotations of SD minus 1. Okay. That will become clear in a moment. So we'll be interested in spherically symmetric solutions today. Next class, I will show you how to break the spherical symmetry and write down all of the solutions. Okay. But we take this general lesson that we always solve the simplest part of a problem first, and the simplest part of this problem is to get the spherically symmetric solutions. And once we have the most symmetric solutions, writing down the less symmetric ones will be natural, as we'll see. Okay. Okay, great. So we'll be interested in spherically symmetric solutions. So I will first solve the positive eigenvalue part. The negative eigenvalue part, as I just said, is an analytic continuation, which I'll write down at the end. So we'll let's first look at the positive eigenvalue problem. Okay, and let's do one dimension. Because one dimension, the Laplacian becomes, so the equation becomes an ODE, and ODE is like this one. We can just write down the solutions, as we'll just do. And from there, we hope to learn some lessons. We hope to make some crucial observations. I will make these observations with some hindsight. I will show you. Okay, let's just start doing it. Okay, so let's write down d squared over dx squared. That's the one-dimensional Laplacian. Acting on psi equal to some kappa squared on psi. Okay, solutions of this we already know. It's just e to the kappa x and e to the minus kappa x. General solution is this linear combination of those two. Okay, general solution is psi equal to a e to the b. Let me write it as sinh and cosh, which is the same information, plus b cos kappa x. Okay. Now, since I just said that I will be only interested in spherically symmetric solutions, what does spherically symmetric solution mean here? Now recall that when you are doing three-dimensional Laplacian, spherical symmetry basically meant that rotations on this sphere S2 don't change the solutions. Right? You have the theta and the phi, so that's an S2, it's a two-dimensional sphere parameterized by theta and phi, and rotations about that does not change the solution. What happened in R2, like when you're doing a planar problem, rotations about the z-axis, that is rotation on this circle, you're moving from one point to another point on the circle, which is S1, okay, doesn't change the solution. So naturally, in one dimension, I want a solution that's invariant under the action of S0, okay. S0 is what? S0 is just defined as x squared equal to 1 such that, x such that x squared equal to 1. Precisely, x belonging to R such that x squared equal to 1. And there are only two different solutions of this, which are 1 and -1. Yeah. So you want a solution that's invariant under this group action. Okay. 1 minus 1 basically means rotation by this sphere basically means you take 1 to minus 1 and or minus 1 to 1. Okay. That's basically saying you take x to minus x. Okay. That's the transformation. So what is the only such solution that's invariant under this? It's just Cauchy's. Right. So the spherically symmetric solution, which I will denote by I naught, since we are in d equal to 1, kappa x, it's a function of kappa x, remember? It's just cosh x, cosh kappa x. Okay. Let me explain this notation. This notation will generalize to arbitrary number of dimensions. 0 basically means that it's spherically symmetric. What we'll see next class is that non-spherically symmetric ones can be arranged in 1, 2, 3 and so on with the same I. D equal to 1 basically means we are in one dimension. Kappa x is because it's a function of kappa x. and this I is some conventional name for these functions. Okay. What will happen is that higher dimensions you get the Bessel functions, Bessel I functions. Okay. Okay. So we learned that this is the spherically symmetric solution in d equal to 1. Now note a very interesting fact about this solution. It is that this solution is just e to the kappa x plus e to the minus kappa x over 2. Right? Now that looks like an average over this S0. Right? Basically what this says, what I'm trying to say is that this is like e to the sum q x, okay, such that q belongs to S0 kappa. When I put a subscript on the S0, I basically means the sphere is of radius kappa, okay, which basically means x squared equal to kappa in this equation. The kappa squared. Okay. So what does this notation mean? This notation basically means that you have to average such that q goes through this set. What does that mean? So what are the only 2 points here? It's just 1 and kappa and minus kappa, right? So you have to do e to the kappa x plus e to the minus kappa x, and then since it's an average basically means you have to divide by the volume of this set. Okay, so basically 1 plus 1, just 2, which is what cos kappa x is. Okay, so this notation is justified. Okay, so what we have learned is that I naught be equal to 1 kappa x is just a spherical average, a 0-dimensional spherical average, as an average over S0 of e to the qx. Okay. Now you might say this is some very complicated way of writing cos kappa x, but why did I write it like this? Because this is what generalizes. Okay. Now let's see why I took this statement. Okay. So since we are done with d equal to 1, let's go to d equal to 2. Okay, let's do 2 dimensions. 2 dimensions is when we start getting the real complication, because a Laplace equation becomes a PDE, and PDEs are not as easy to solve as ODEs. This is the PDE you must solve, right? Now at first look, it looks very complicated. Even if you say I want a spherically symmetric solution, which is just a function of x squared plus y squared, or equivalently function of just rho, where rho is square root of x squared plus y squared, it's still a complicated problem. Okay? But I claim that I naught of d equal to 2 kappa rho equal to e to the q vector dot r vector, where r vector is just some vector in this 2-dimensional plane and rho is the modulus of that r vector. So rho is modulus of r vector such that q belongs to S1, because there remember it was S0, which is d minus 1, because we have 1d. So here d minus 1 is just 1 kappa. I claim that this is the solution. Okay. Actually, we can do more. Let me just do this in arbitrary dimensions. Let me just look in d dimensions. This 2 goes away, you just write a d. And this becomes d minus 1. This I claim, and in d dimensions I'll call the radial coordinate as r. Only in 2 dimensions I'll call the radial coordinate rho. Okay. This I claim is a spherically symmetric solution of the d-dimensional Laplace positive eigenvalue problem. Okay. Let me explain why. Firstly, I have to explain that this is spherically symmetric, because this side I just wrote kappa r, not kappa r vector, right? So I have to show you that this is a function of just modulus of r. But that's very easy to see, because what am I doing here? What does this average mean? Let me explain this average. First of all, S kappa d minus 1 basically is what? It's the set of all points in Rd, xd belonging to Rd. Remember that if d was 3, x comma y comma z is the coordinate in R3, and the S2 or the two-dimensional sphere is just the requirement that x squared plus y squared plus z squared equal to kappa squared, and in general dimension is just I equal to 1 to d xi squared equal to kappa squared. That's the d minus 1 dimensional sphere of radius kappa. Okay. So what this means is that you have to take q to be every such point in this d minus 1 dimensional sphere. Okay. Let me illustrate that with 2 dimensions. Okay. So S2 is just what? S2 kappa is parameterized by theta and phi, right? 2 coordinates. So q vector can take any point on this S2, right? So q vector dot r vector, I can choose r vector to be any point on this sphere. Okay, maybe I'm confusing you guys. Let me explain this properly. Let me do I naught be equal to 2 of kappa rho, which is just e to the q dot r, q belonging to S1 kappa. S1, remember, is just circle. The one on top basically says it's a one-dimensional manifold, and the circle is a one-dimensional manifold because on a point the circle is just a line, right? Okay. So Q, when it belongs to S, so you have some R2, which is where you're solving the problem, two-dimensional plane, x, y. This R vector, basically I have to show that this expression is independent of R vector. Say I choose R vector here, say that is R vector, okay, and say this is Q vector, and say the angle between them is phi. Okay, this spherical average means what? It means that Q dot R is just QR, Q rho, cos phi q, and spherical average means that this Q vector has to go to every point on the r-dimensional sphere, on the one-dimensional sphere, which is the circle, which means I have to integrate over the full circle. Okay, and since it's an average, I have to divide by integral over 0 to 2 pi d phi q 1. Now that's just 2 pi. Write it 2 pi. Okay, and that's it, right? So now this is obviously dependent only on the magnitude of r. Why? Because I chose an r vector and then I chose a q vector which is at some phi q, and then I said I'm averaging over all such q vectors. I'm taking this q vector, this q vector, this q vector, and so on and so forth, and averaging over all of them. I'm dotting with r and then adding up, exponentiating and then adding up. So it doesn't matter even if I choose my r vector here, right? Even if r vector was there, I'm taking every q vector and dotting it, and q dot r, and then exponentiating. So it doesn't matter. Okay. So then it's clear that this is spherically symmetric. Okay. Secondly, I have to show that this solves the Laplace equation, which is actually very easy to see because grad squared. Remember that this grad squared is in any dimension, so this is del L x1 squared plus del L x2 squared plus del L x3 squared all the way till del L xd squared. I naught of b comma kappa r is equal to grad squared by the definition of I naught b comma kappa r, which is q dot r such that q belongs to s kappa d minus 1. But then grad squared is a differential operator on r. This spherical average is over the coordinates of q, right? You remember in the two-dimensional example, I did an integral over d phi q, where phi q was the angle that q substituted with respect to r. Okay, and r I just showed it doesn't matter where you choose r. So say I choose r along x-axis, then phi q is just angle of the q vector from the x-axis, right? And that average is over phi q. So it doesn't matter to the grad square. So the grad square can just be taken inside. So you just get grad square e to the q dot r, q vector belonging to S minus 1, S coupled e minus 1. And grad square e to the q dot r is what? Q square. Right? That must be easy to see, right? Because grad square e to the q dot r is just divergence grad e to the q dot r, grad of scalar function. Okay, you can do this in Cartesian and check if you want. It's a divergence of e to the q dot r. Exponential will come out anyway, and then you have to do grad of this bit. But grad of this bit is easy to do because there's just 2. Right? That's easy to see in Cartesian. And then divergence of this, since this is constant, so it will be divergence of this times that, but divergence of this is 0, plus e to the q dot r times, plus q dot grad of this, but grad of this we already computed, is just q times e to the q dot r. So this is just q squared e to the q dot r. Right? 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 Okay. So grad squared will just give you q squared. So this is equal to q squared e to the q dot r. Q belongs to S kappa d minus 1. Okay, but q squared is iterator because q squared is just, because q belongs to the kappa radius kappa sphere. Okay, so q squared is just kappa squared. Okay, so that's just kappa squared, and kappa squared comes out. So this is just kappa squared e to the q dot r, q belonging to S. Which means grad squared I naught, or grad squared this, is equal to kappa squared that. Which means it solves the positive eigenvalue problem of the Laplacian. Okay, so I'm done. I'm done solving the positive eigenvalue problem, at least for the spherically symmetric solution. So what have I done so far? I have basically found all the spherically symmetric solutions, because there is only one spherically symmetric solution. Okay, that's a theorem you need to show. We'll eventually show it if we get there, that it's a uniqueness theorem. We'll basically show that this is the only solution. Solution is unique. Okay, but for now we'll be content with the fact that we have found the spherically symmetric solution of the Laplace equation. Okay, now this is a bit abstract because I've written down these angle brackets and said you have to average over the sphere. Let me write this down a bit more explicitly. One dimension we have already done, so let me do d equal to 2. That also I just showed a bit. Right, so let me do d equal to 2. D equal to 2, positive eigenvalue problem, remember, I naught of d equal to 2, kappa rho. This is what people usually denote it as I naught of kappa rho, capital I naught of kappa rho, and this is called the Bessel I function. Okay. Remember that by our definition, this is just equal to spherical average of e to the q dot r such that q belongs to this d minus 1, d is 2, that's 1, kappa. Right. What does this expression mean? This expression means that q belongs to the one-dimensional sphere or the circle. Q belongs there, and we can choose r vector wherever we want. So I choose r vector along the x-axis. Okay, and the angle between q and x-axis I will choose to be phi q. Then e to the q dot r is just e to the kappa. Remember that modulus of q is just kappa. Rho, which is the modulus of r, and then cos by q. And then q has to go through this full sphere, which means I have to average integrate over the full phi q. And since it's an average, I have to integrate 0 to 2 pi q. And that is just I naught of kappa rho equal to, this is just 2 pi, so I'll write 0 to 2 pi d per q over 2 pi d to the kappa rho constant. And that is the Bessel I zero. I will also sometimes refer to this as the cylindrical Bessel I. You'll see why, because these come up in cylindrical problems. Okay, when we start solving problems, you'll see why this comes up in cylindrical problems, as opposed to what I'm going to discuss next. So d equal to 2 is done. Okay. Remember why the Bessel functions are showing up here. If you've done some mathematical physics course earlier, you would have seen you write down the Helmholtz equation or the screen Poisson equation, and you do variable separation. Then you do the theta phi problem, which gives you the spherical harmonics, and then you do the radial problem, which gives you Bessel functions, right? But we didn't need to do variable separation and then some Frobenius series or whatever. We just wrote down an answer, right? And that's the power of this way of thinking about it as a spherical average. Note that this is an integral representation. If you've seen this mathematical physics course, you would call this an integral representation of the Bessel function. You would say, oh well, you should really write down a power series for this to be useful. But you can write down a power series, right? All you need to do is expand this exponential in a Markov-Taylor expansion. Okay, which is just what? Exponential is the summation n equal to 0 to infinity 1 over n factorial kappa rho to the n cos pi q to the n. And then you have to do integral of cos pi q to the n, which is an integral we learned to do in undergrad, for example. And once you do that integral, you have the power series expansion, which you can match with the Frobenius way of doing it. Okay. But more importantly, you have an exact expression. The power series expansion you can count. If you're doing Frobenius, you will do like 2 or 3 orders and then you give up. But then here you have an exact expression, okay, which you can do asymptotics with. You can ask what does it look like at large rho. If you have solved like a radiation problem, for example, and you got this Bessel function, say, and you want to ask very far away from the radiating source, what do I feel? Then you would have to do a large rho expansion of this. Or then you could ask very close to the radiating particle, if you sit in the near zone, what does it look like? Again, you can do an expansion of this. Okay. So asymptotic expansions can be done very easily. Moreover, another thing that you must notice is that while writing a power series expansion, say you are solving the 1D problem with the power series expansion. Okay. Say you are solving d squared by dx squared of psi equal to kappa squared of psi. You didn't know about the exponential functions, and you start doing power series expansion. You will of course get the power series exponential. You learn some things, but you miss out on insight. You miss out on the fact that decaying exponential, growing exponential. In problems, you should not keep the growing exponential. You should only keep the decaying exponential, and so on and so forth. All these are insights that you start, that become second nature to you once you realize it's an exponential function, right? If you don't, it becomes very tricky to work with the power series expansion. Then you must ask, oh, does this power series expansion grow, or does it converge even, or does it diverge, and so on and so forth. The questions become complicated. Similarly, here also, if you start writing a power series expansion, it gets very tricky to understand it. Now, of course, there are problems in which the power series expansion is useful, very useful indeed, and that way you can derive from here. Okay, so you must not look at this as an integral representation, which is probably not useful. It is, as we'll see, the most useful way of thinking about Bessel functions. Okay, and the answer I wrote down here as a spherical average for all dimensional Bessel functions is again an integral representation, because the q vector belongs to SD minus 1 kappa, which means you have to integrate over all the coordinates which label the higher dimensional sphere. Should be some integral representation. So let's do it for d equal to 3. Higher d I won't do, you can do it if you want. Okay. D equal to 3. I naught. So d equal to 3, I naught, d equal to 3 kappa r is what people usually call I0 kappa r, which is called spherically Bessel I. Okay. In mathematical you can implement it with spherical Bessel I0, which by our definition is just e to the q dot r such that q belongs to S2 kappa. S2 is parameterized by theta and phi. Since this does not depend on what direction r is in, let me choose r to be in the most convenient direction, z direction, say, z hat. So if r is r times z hat, e to the q dot r can be written as e to the mod of q is kappa, mod of r is r, a vector is r, and then q vector is just some vector. Q vector dot z hat is just cos phi q, cos theta q. Right, so the situation I'm thinking about is something like this. That's the z hat axis. Q vector is somewhere here. Okay, this is some kappa dimension sphere, and its polar angle is theta q, and its azimuthal angle is phi. Okay, so q dot r will just have the polar angle. Okay, and you have to integrate q over the full sphere, which means theta q has to go from 0 to pi, polar angle goes from 0 to pi, and the azimuthal angle should go from 0 to 2 pi, and the correct measure, remember, is sin theta dq, theta q, and then you have to divide that over 0 to 2 pi, 0 to pi, d theta q, 0 to 2 pi, sin theta q, theta q. This is just volume of sphere. Volume of sphere is what? This integral is what? 4 pi. This integral 4 pi. So this whole thing, actually this has a closed form expression. Spherical Bessel I0 has a closed form expression. I naught of kappa r is just equal to 1 by 4 pi. But this does not have a phi dependence, so this phi integral can be done, so that gives a 2 pi. So that's a 2 pi by 4 pi, that's a half. And then you have to do a theta integral, 0 to pi, d theta q, sin theta q, e to the kappa r, cos theta q. Okay? But this is also doable integral. Let's call cos theta q. So this is just d cos theta q with a minus sign. That minus sign I can pull into the limits, make this minus 1 to 1 instead of 1 to minus 1. Okay. And this is a doable integral because this is just 1 by kappa r e to the kappa r minus e to the minus kappa r. So this is e to the kappa r minus e to the minus kappa r over 2 kappa r, which is just sinh kappa r phi kappa r. So I naught of kappa r equal to sinh kappa r over kappa r. This is some expression you can find in Jackson, for example. All of these are expressions you can find in Jackson. Okay. So we have gotten all the spherically symmetric solutions of the positive eigenvalue problem. Okay. Now if you are asking for non-spherically symmetric solutions, it's just putting an index L instead of 0. Okay. That's also easy to do. All you need to do is differentiate these I0s. I'll show you how to do that next time. Okay. But for now, let's only concentrate on spherically symmetric problems. Say you're only solving spherically symmetric problems, like charged ring or charged sphere, something like that. Okay. So we're done with the positive eigenvalue problem. Let's do the negative eigenvalue problem. Okay. Negative eigenvalue problem. Sorry. Okay. Okay. Negative eigenvalue problem is just what? Rad squared I equal to minus kappa squared sine. But that's just I kappa whole squared sine. Which means it's just an analytic continuation. All I need to do is just make kappa imaginary in all the earlier solutions. And this analytic continuation can actually be done very trivially. Okay? Which means, so the negative eigenvalue solutions are what we call the Bessel J's. Bessel J d kappa rho is just equal to I naught d I kappa rho. Okay. Which is just equal to spherical average e to I q dot r such that q dot s kappa d. Now you could have, for example, repeated this whole analysis for negative eigenvalue instead of using this analytic continuation. For example, you can do d equal to 1 first. You'll find that the solutions of sine are sine and cos, and then you want the spherically symmetric solution. You'll keep the cos, and the cos is exactly in this form, and then you generalize it, and then you check that this is the correct answer. Okay, so d equal to 1. This gives cos kappa x, which is spherically symmetric, and it solves Laplace equation, Laplace negative eigenvalue equation. D equal to 2, that's the spherical Bessel J, cylindrical Bessel J, or I think people usually call it modified Bessel functions. Spherically symmetric modified Bessel functions. Okay, so J0 D equal to 2 kappa rho, people usually call J0 over kappa rho, which just like we wrote the I, we can just write this down as 0 to 2 pi d pi q over 2 pi e to the I. This I is what's different now. I kappa rho cos pi q. That's called in Mathematica you just implement this as Bessel J0. I'll avoid this nomenclature as modified Bessel functions and incomplete Bessel functions and incomplete modified Bessel functions and so on and so forth, because those names are not suggestive. I'll use these suggestive names, Bessel J, Bessel I. Even here, you have to just remember the fact that I is the positive eigenvalue problem and J is the negative eigenvalue problem. That much you can remember. Well done. I and J are some conventional things. I don't want to change up those names, so we keep those names. D equal to 3. We already found I naught D equal to 3. It's just sinh kappa r by kappa r. So you have to do an analytic continuation of that. But remember, sinh, if you make it an sinh of I kappa r, is just I sin kappa r divided by I kappa r. So the i's cancel. So it's just sin kappa r by kappa r. So I naught D equal to 3 kappa rho is what one usually calls the spherical Bessel. So this in Mathematica is implemented as spherical Bessel I0, which is just sin kappa r by kappa r, which one usually calls sinh kappa r. Okay, so we're done. We're done with the positive eigenvalue problem first, which gives the I. Sorry, J. This is J0. So we're done with the positive eigenvalue problem, which gives us the i's. Let's only talk about spherically symmetric. So positive eigenvalue problem gave us i's, negative eigenvalue problem gave us j's, zero eigenvalue problem is this Laplace equation, which you already solved and got r to the L times y LMs. So we are basically done with the eigenvalue problem of the Laplacian spherically symmetric. Non-spherically symmetric, next step. Okay? So nice. Let me stop here with today's class. Next class, before doing the non-spherically symmetric problems, what I want to do is to take just what we know so far and to solve some electrostatics problems with it. And the first problem I want to solve is the problem of a charged ring. Okay? Say you have a ring. The following is the problem. Say you have a ring of charge q on the xy plane. Okay. They just kept here. I mean, you can choose the plane of the ring to be the xy plane. It's just there. Question is, what is the electric field, or equivalently, what is the electric potential produced everywhere due to this ring? Now this is a Griffith's problem, but a special case if this is the Griffith's problem. In Griffith's you might have solved this problem in the for the electric field on the axis, right? By this, you're taking a dz and then you're doing an integration, and then you integrate over the full circle and you get the electric field on the axis. But some of you might have wondered, how do you get the electric field away from the axis? And that's the problem I solve next time. Okay, that, as we will see, will involve Bessel J0 equal to 2. Okay, the cylindrical Bessels. Okay, so let's stop here.